Hello everyone, this is our presentation of mixture of Bernoulli. We have 4 parts: introduction, a mixture of Bernoulli, the program and results. First, this is introduction. We aim to fit a mixture of Bernoulli models to the distribution of images in the MNIST dataset and use the generative distribution for clustering, and generating new images. The main idea is to estimate the weights and expectations that maximize the likelihood function given the observed images. The likelihood represents a probability for all image points to be generated by the learned mixture of Bernoulli. Since the multiplicative form of the likelihood is difficult to handle, we use log so that products become sums. Furthermore, introducing the latent variable z simplifies the whole process. Last but not least, by applying Bayes' rule, we ultimately solve the problem with the EM algorithm. First, we have 3 assumptions. The first one, a MNIST image X is composed of D independent binary pixels Xi. And the second one, the training dataset is composed of N images. And the third one, there are K possible Bernoulli distributions to form the mixture. Each pixel can be modeled with a Bernoulli variable with a possibility or expectation mu ki, which is the element of mu k. So we can have a joint distribution of X given the mixture model like this, and the sum of wk equals 1, and each wk represents weight, and this is a joint distribution of each Bernoulli distribution, and this is the linear combination of Bernoulli distributions. And since every x is independent and follow the same distribution, if we want to find L theta, we just multiply every pxi, and we can get our target function L theta. But multiply is too complicated, so we put log on both sides of the equation, so we can get this log likelihood. It's just transform multiples into sums, and we have log in here. Just substitute this in this, we get this. But this is still complicated because we still have some multiples. So we introduce the latent variable z. What does this mean? If and only x follows the Bernoulli distribution with mean mu k and zk equals 1, otherwise zk equals 0. And by definition, we get the marginal model, the conditional model, and joint model like this. And we just substitute those into this. We can get this format. And this is so simple because we don't have multiplies, we only have sums. And if we have, like we know every zk, we know every xi, we can easily get wk and mu k to maximize L theta. And theta is a combination of wk and mu ki. And finally, we get to the EM algorithm. In the E step, we want to get RNK, and RNK represents the responsibility that the component K generated the data point xn. And based on Bayes' rule, we have this equation. And based on this, we finally have the expression of Rnk. It is easy to get. And in the M step, we have Rnk already, so we have the new Wk and new mu Ki, and we just repeat the E step and the M step until it converge. We can get our result.